Hi, my name is Eric Fierstein.
And my name is Kevin Shannon, and this is our project for spring of 2017 here at Rowan University for the engineering clinic program. The project is titled Robust Sparse Representation in Facial Recognition, and essentially the objective here is to analyze facial recognition through multiple different methods. Last semester we analyzed the KNN classifier method of facial recognition and tested the success rates for clean images and noisy images. And our objective here this semester is to create an algorithm in MATLAB implementing sparse representation, that method of facial recognition, and essentially obtain higher success rates for this method and prove why sparse is a more efficient method and why it can also deal with the noisy case of images much better for facial recognition.
So facial recognition is simply one type of biometric recognition system. Biometric recognition systems are useful for a variety of reasons, but their most common use is for security purposes. For example, you could use a biometric system, such as a fingerprint scanner, to open up a locked door, or you can use facial recognition to scan a crowd for potential criminals or terrorists. So facial recognition is not the only type of biometric system. Common biometric systems include facial recognition, retina scanning, and fingerprint scanning. While each of these systems has their own method of implementation, they all follow the same basic algorithm. The algorithm begins by reading sensor data and creating a feature vector from this data. This is done multiple times across multiple subjects to create a trained database of feature vectors. Once the database is complete, a test feature vector can be run through a classifier and compared to the database. The classifier is in charge of deciding what subject from the database the test feature vector belongs to. In our case, we implemented a sparse representation classifier and a KNN classifier to compare the two results. A brief numerical example may provide more information regarding the algorithm given in the previous slide. In this example, the A matrix corresponds to a trained database where each column of the A matrix corresponds to a different subject's feature vector. The Y vector is the test feature vector that will be compared to the A matrix. In the top system, KNN, it takes the L2 norm distance between the Y vector and each column in the A matrix. From this plot, it's easy to see that subject 4 has the lowest distance, so the classifier would return subject 4 as the correct subject. The bottom method, sparse representation, solves the equation AX equal to Y using the CVX toolbox in MATLAB and taking the L1 minimization of X. The X coefficient is then plotted, and it is seen that the highest coefficient corresponds to subject 4. The classifier then selects subject 4 as the correct subject.
Okay, so a few constraints of this project were that the computing times for L1 minimization and linear combination problems were very long. To kind of get around this, we used the high-performance computer here at Rowan to kind of minimize the amount of time it took to compile our code and run through the L1 minimization. Another constraint we had was that the algorithm for sparse representation should produce higher success rates than that of the KNN model, and we implemented our code and adjusted our algorithm to try to achieve those success rates. And another big part of sparse representation is that it should be more robust to noise. So one thing we looked out for was really making sure the algorithm for sparse was more robust to noise than the KNN model, and that we achieved those.
After implementing both the KNN classifier and the sparse representation classifier with the AT&T database, it was found that the KNN success rate was 93% and the sparse success rate was only 71%. Our future work will include changing constraints in the L1 minimization problem to get the sparse representation classifier up to the same success rate as the KNN classifier. Once this is done, we will add noise to both systems and hopefully observe that sparse representation is more robust than the KNN classifier.
Our clinic team would like to thank Dr. Ravi Ramachandran as our head advisor for this project. We would also like to thank Dr. Nidal Boyanaya for her consulting throughout this project.
We would also like to acknowledge the SNR Estimation Clinic with the members of Peter Aulmate and Mitchell Rudy. We worked in close contention with them throughout the semester, so we felt it was important to mention them as well.